Great. So yeah, these are some results from my PhD. And the starting point is really the observation that modern ecosystems are dominated by a large variety of different animals. We have sharks, we have fishes, we have different kinds of marine tetrapods which are secondly adapted to marine lifestyle. And facilitating this is the fact that most of these animals don't compete for the same resources, so they niche partition their environment. Supporting this recent paper from Kelly and Montani demonstrated that that morphological convergence in marine tetrapods is driven by trophic convergences. So in other simple words, animals that feeds on the same thing are more likely to have a similar structure in their skull, lower jaws, and teeth. So I am interested in fossil animal, and so this is quite a powerful tool for me, because if we can turn this idea backwards in the fossil record, looking at the morphology, we may be able to assess if animals in the past, in past ecosystem, were as well niche partitioned in their environment. Clearly, in order to do that, we need an example of an ecosystem which is well preserved, and what I'm looking at is the Jurassic. In particular, the Sub-Boreal Jurassic Seaway, which has been deposited in the UK, in what is now the UK, across the Callovian towards the beginning halfway through the Tithonian. This seaway was two formation makes part of this. The oxoclay formation and chimeric clay formation and strata in between. There are multiple reasons why these are perfect case of study. First of all, they were deposited in the same seaway, so we can have a slice through time of the same fauna. The dog fauna is well documented, and we have a evidence of coexistence of different clays. So meteorhingids, plesiosaur, and ichthyosaur are found in the same strata. Furthermore, an additional reason is evolutionary. So we have evidence from analyzing the Callovian and the Chimerigian Tithonian fauna that these were quite different. So in which way? So for example, we had the disappearance of mid-sized pliosauride pretty much in the Oxfordian, decline of some fish-feeding meteorhingids, diversification of macropredatory meteorhingids called Geosaurinae just at the beginning of the Chimerigian, and diversification of Ophthalmosauridae. Now, all these trends are well studied within their individual group, but there has been a lack of study of all these animals as an evolutionary fauna, which is where I come from. So what we propose to do is looking at the feeding ecology of this animal and see how the functional space of occupation of this animal works. In order to do that, we adopted a well-established method. We expanded a data set of character originally written by Tom Stubbs. I expanded with the some continuous characters and used 6 discrete characters. Score for 62 specimens, subdivided in 5 subfamilies, which is a resolution in a taxonomic resolution that previous studies haven't done. Unfortunately, I was only able to use 2 time bins, but we'll talk about that later. And all these characters, the continuous characters were firstly zeta normalized, and then all the data set was transformed in a similarity matrix using Gower coefficient, and analyzed with principal coordinate analysis. And that's what we got. So bear with me here, there's a lot going on here. Animals found in the oxoclay are labeled with a diamond. A dot is for animals found in the chimeric clay, and the groups are color-coded with different colors. We can immediately see, if we look at the oxoclay, that most of the diversity of the entire data set is made up by animals in the oxoclay formation. Interestingly, we have 2 groups of pliosaurids. These are longirostrum form, species of the genus Marmonectis and Peloneustis. and similar animals. And then separated, we have Pliosaurus andrewsi, not really Pliosaurus, and then Leupleurodon and Simolestis on this area. So I forgot to say that this broad area is characterized animals which have a short and deep mandibular symphysis, and large adductor musculature, and high mechanical values. So generally macropredatory animal. The exception is clearly plesiosaurs, which have very short mandibular symphysis, but they are this long. So they are morphologically similar to pliosaurs, but there's a size issue with that. And on the other side of the graph, we have animal with a long mandibular symphysis and shallow and low mechanical values, so most likely piscivorous form. What I'd like you to see here is that we have a partial overlap between Geosaurines and pliosaurs, but if we look through time, that overlap, it's not synchronous. What does that mean? So in the chimerical formation now, Geosaurine expand their morphospace occupation, which goes well with what we know from the study of the group. The pliosaurids converge towards one single genus, Pliosaurus. We have a strong reduction in morphospace occupation of Telosaurid down here. So these are Machimosaurus animal belonging to the genus Machimosaurus, and we have the expansion of Ophthalmosaurid space occupation. Now, summarizing this, we see that phylogenetically closely related taxa clustered together. There's minimal overlap, which may be indication of niche partitioning. We also recover all the main evolutionary trends that I've highlighted before. However, this is not enough, probably not enough to convince you, because we have that this data set heavily relies on complete specimens. So we don't have a great time resolution. We only have 2 time bins. And the way to fix that, in our opinion, was to look at a teeth. So this has already been done. I modified quite heavily this Massare study. And the advantage of looking at dentition is that tooth morphology has been demonstrated to be closely representative of feeding ecology, in both modern and extinct animals. The teeth of marine reptiles are fairly diagnostic to genus and specific level, so we have a good taxonomic resolution as well. With a better fossil record of teeth because they are more easily preserved. That means that we have more specimens, and that means that we have a better time slicing. So I have built up a new data set with less continuous characters, 23 discrete characters, 121 specimens, subdividing 4 time bins. I've done all the same procedure with the characters, normalized, transformed into a similarity distance matrix, and analyzed on using principal coordinate. And that's what we have. This time, different shapes represent different taxa, excluding the dashes. Dashes are still unidentified specimens. We recover all the gills that Massare found. So on the top left, we have Durophagus animals. So Lemisuchus, Metorhynchus, Machimosaurus are up there. And then the clade Torvoneustis. We have Leupleurodon occupying this area here. The trihedral teeth of Pliosaurus are all there. And on the bottom left, we have animals that falls in the category cut, and the Pierce categories are just down there with Palaeontology here, Ophthalmosaurus, and some Longirostrine telosaurids. Now, let's slice that through time. Again, in the Callopian, we have a large disparity. A lot of space is occupied by telosaurs, which have quite different ecologies through time, so Piscivorous taxa and Durophagus taxa. We have again sort of a distinction between Longilostrine Pliosauride, so Palaeoneustis is here, Marmonextis is here, and then Pliosaurus andrewsi and Leoplerodon are up here. Lot of cut space is occupied by Meturynchids, Geosaurians actually. If we go through the Oxfordian, there are very rare specimens. Most of them have been overlooked. I have a I have idea of what these animals are, but this is another story for another time. But what we see here is that a reduction of morphospace space of occupation of Pliosaurids. Only one type of Pliosaurid survived through the Callovian-Oxfordian boundary. There's no more Piscivorous Talosaurids. We have an initial expansion of Geosaurin taxa towards the morphospace space occupied by animals like Torvoneustis in the Kyma region, and we persist to have Macrophagous Talosaurids. In the Kyma region, things becomes more fun. We have a strong radiation of Geosaurins, Torvoneustis, an undescribed taxon from the Oxford Museum, and animal down there like Geosaurus, Dacosaurus, and Plesiosuchus. The purple triangles are taxa belonging to the genus Pliosaurus. However, we have another kind of other types of teeth belonging to Pliosaurids, which are yet undescribed, which is quite interesting. So we may be underestimating the diversity of Pliosaurids in the Kyma region. And here are taxa probably belonging to something similar to Brachypterygius. And the Tithonian, all we can record is a strong expansion of ophthalmosaurid space occupation, and everything else kind of stays unvaried. Unfortunately, we have little sample from these strata. So if we summarize this up, we can conclude that the oxoclay and Kymergic lake formation had ecosystems were quite different each other. Both the analysis of the lower jaw and the teeth concur that the Callovian is the most diverse assemblage. We have a strong phylogenetic signal which controls the distribution of taxa, which is which is probably an indication that different groups were doing ecologically different things. And that is evidence of probably niche partitioning. So there's no significant overlap at the same period of time, which means that animals were doing mechanically and ecologically different things. We recovered all the evolutionary trend that has been highlighted in the study for individual clades, but teeth allow us to give a better timing for some of this. So Geosaurin radiation probably started earlier than thought in the Oxfordian and then exploded in the Kyma region. The decline of small-bodied Pliosaurid and Talosaurid, Longilostrine Talosaurid is already gone, so these animals are already gone by the Oxfordian. And tooth analysis suggests that we are probably underestimating the diversity, or at least the functional diversity of marine reptiles in the Oxfordian and Tithonian, at least locally for oxoclay and Kymergic clay formation. Overall, the teeth analysis and lower jaw analysis suggest that partitioning of functionally important morphological feature could have been a factor to facilitate the ecosystem, the existence of highly diverse assemblages as it is in modern ecosystem. That's few people to thank, and any question? Thanks for your attention.